volume is actually not conserved, and that's where this idea of fractals comes in. So fractals capture the idea that volume isn't actually conserved when we bring two particles together. And that's because when we bring two particles together, the diameter that we consider for that new particle includes stuff that isn't either of those particles, but is the fluid that was around them. So here are the equations describing this idea. So N is the number of primary or core particles in the flock, and we're going to raise that to some crazy exponent, 1 over pi fractal. And the dCp is the diameter of the core particle. Okay, so let's look at the equation for volume. So the volume of our resulting flock is equal to the volume of the original particle, like the original clay particle, times the number of clay particles raised to the power of 3 over pi fractal. Now, stare at that equation for a little bit. If every clay particle that collided somehow attached really, really tightly and essentially was slowly forming this sand grain, what would pi fractal be? This is the case where there's no water in between the clay particles. They just all like line up and form this solid, this new solid. What's pi fractal in that case? This is the case where volume is conserved, where when you have two clay particles, you join them together and the volume of the new entity is exactly 2 times what it was originally. So pi fractal would be 3. And the case where this really happens is if you're studying rain droplets forming in clouds, and there's an aggregation process that's happening there too, like flocculation. And in that case, 2 tiny rain droplets collide and they form a new rain droplet. And the volume of the first little droplet and the volume of the second little droplet add up to the volume of the final droplet, right? That's beautiful. That's what we would love. And that's the case where pi fractal is 3. Volume is conserved. But you see our flock that's formed over here? So our flock slowly adds more and more pieces on. And as it adds more pieces on, it incorporates more and more water into what we now call the flock. And that means that the volume of the flock includes a bunch of new water. So the volume of the flock is greater than the volume of the subunits. Okay? And that keeps on happening. Every time the flock grows a little bit larger, we get more and more water incorporated into the flock. And so in that case, the flock, what is the flock mass doing over time? The total mass of all the flocks in our flocculator, as they grow in size, what happens to the total mass of flocks? It increases because there's more and more water associated with those flocks. Like when I added this second flock on, the new diameter that we would draw to include everything in that flock includes a whole lot more water. So adding that second piece on adds a whole lot more water to our flock. And so volume is not conserved, flock mass is not conserved. And we can describe this new crazy geometry of these things that are just aggregating, where each time it aggregates, you get more water embedded into the flock. We can describe this using this simple geometry where pi fractal is no longer 3, it's going to actually be closer to 2. And it also means that the flock density decreases as it gets bigger. This is actually quite disconcerting. The whole point of getting flocks to collide is so that they settle faster. Remember we did that, we have that terminal velocity equation, and we saw that if we increase the diameter of a particle, it settles faster. So that was great. We're getting flocks to collide, they're getting bigger, they're gonna settle faster. But there's another term in that terminal velocity equation, and that is what's the density of our particle. And now we just learned that our particle is getting less and less dense as it gets bigger and bigger. And this is indeed the case. The flocks do get less and less dense. And so we have this question of, is this going to work? Is flocculation going to actually get us particles that have a higher sedimentation velocity? I don't know. Okay, that was just background. So how many core particles might there actually be inside a flock? So here's our equation where I've solved for the number of primary particles. I've taken the equation that's up there at the far right. I've solved it for n. And we have, let's take our case that was kind of like the problem that you all worked on. Let's assume the core particle is 5 micrometers in diameter, and let's assume the flock is 3 millimeters in diameter. The fractal dimension is about 2. And if you plug that into the equation, I get about 360,000 particles in a 3 millimeter diameter flock. And so this isn't the billion particles at all that I talked about a couple slides ago. We don't get nearly 1 billion particles in a flock. We get less than 1 million, but close to 1 million. And it's because the flock is not a sand grain when it's done. So this is our big question. Is this monstrous flock that we've created actually going to settle faster? And I think I can do this yet, and then we'll call it a good day. So here's the equation for terminal velocity of a particle. And this is the case for laminar flow, Stokes' law. And we see that there's this rho flock minus rho H2O. That's the difference in density between the particle that's falling in the water and the water itself. And it's that difference that gravity is grabbing a hold of and using to pull it down or push it up, depending on what the densities are. That's called the buoyant density. The difference in density between the particle and water is the buoyant density. And so what I've done is I've plotted the buoyant density of some hypothetical flocks with different fractal dimensions. So the one that's like really fun is the brown line with the fractal dimension of 3. With the fractal dimension of 3, what you see, look, there's the equation. And when the fractal dimension is 3, that term just goes away. There's 3 minus pi fractal, that's 0. And that means that there's no influence of the diameter of the flock. And that's because the flock is always just solid. It's clay particles that are right next to each other, tight up against each other, forming a sand grain as they grow bigger. So that's fractal dimension of 3. And then as you decrease the fractal dimension, the resulting flock gets less and less dense, and it's dramatic. Oh, I think we didn't define, why does it start at 1,650 kilograms per meter cubed? Where did that number come from? Did Monroe just invent 1,650 kilograms per meter cubed? Anyone know? That y-axis is the flock density minus the water density. So what is that number? I'm cheating. No, I'm not cheating. It's the density of a clay particle, which is 2,650, minus the density of water, which is 1,000. So 1,650 is the buoyant density of a clay particle. So I'm starting with clay particles and looking at what happens, because clay is like the dominant thing that's going to be in a surface water. Okay, So what we see is blue line, red line, as the fractal dimension it decreases, the density decreases a lot. And so we have this really big question of, are we going to win or are we going to lose? Because if this effect is too big, it will mean that we're going to create big flocks, but they're not going to settle. Happily, here's the next stage in the story. They still settle faster because the diameter effect ends up being more important. So here's the terminal velocity of different flocks as a function of size and as a function of the density of the core particle. So there's the blue line is a clay particle with a core density of 2,650 kilograms per meter cubed. And as the flock increases in diameter from, say, 5 micrometers up to 1,000 micrometers, up to a millimeter, where we can easily see it, the terminal velocity does increase. And it might increase up to 10 millimeters per second. So that's cool. In our original equation, the exponent for the diameter effect was squared. Now we have this exponent of pi fractal minus 1. So if pi fractal is 3, which is what you would normally assume, then we get our original equation. But if pi fractal is less than 3, then the effective diameter isn't as helpful as we were hoping. And I suppose, look, if pi fractal was 1, what would happen? If pi fractal were 1, then there would be no impact of increasing the flock size. It would still settle really, really slow. So if pi fractal had been 1, sedimentation tanks would not work. Isn't this interesting? Pi fractal is not 3. If it were, sedimentation tanks would be amazing. If pi fractal were 1, they wouldn't work at all. And we are in the middle ground where fractal dimension is about 2. And sedimentation does work. I wouldn't say it's amazing, but it's great, okay? And we get a particle that would have settled at 0.01 millimeters per second and would have taken forever to drop. And now all of a sudden it can be dropping at a millimeter or maybe even 10 millimeters per second. And that's a nice clip. Okay, it's still slow. You can walk faster than this, but it's settling and we can remove it using a sedimentation tank. So that very bottom end, that's the depressing part of the curve where things are settling really, really slow. That's why flocculation is really, really necessary. The purple line is how fast a particle has to be dropping in order to be captured by the plate settlers in the sedimentation tank. And we'll get to talk about them eventually. So that's a little bit more than 0.1 millimeters per second, which means that it looks like we could capture a flock that is bigger than maybe 20 or 30 micrometers in diameter in the sedimentation tank. So that's at the top of the sedimentation tank. In the bottom of the sedimentation tank, there's a higher upflow velocity, and that's a millimeter per second. And flocks have to be bigger than, say, like 150 micrometers, right here, 150 micrometers, or if they're lower density flocks, several hundred micrometers, in order to actually be able to ever get to the bottom of the sedimentation tank. Otherwise, the upflow velocity is going to be too high and they're just going to get pushed back up into the plate settlers again. And one more observation here. The model, the equation that we have on the bottom of the screen, this equation, does take into account the fractal dimension effect on density. And just assumes that our flock is still a sphere, an impermeable sphere that has a lower density. But we're ignoring the fact that the flock is actually porous. There's water in the flock, there's paths where water could actually flow through the flock. And so when the flock is dropping through the water, it's going to drop a little bit faster than what we're predicting because there's some flow right through the flock. We have not yet taken that into account. I think it's a pretty small effect, but we're not modeling that here. Yeah, so this is just saying that a flock of 400 micrometers in diameter would be big enough to hang out in the bottom part of our sedimentation tank. And indeed, that's kind of what we see. So this model, it does make reasonable predictions about the size of flocks and how fast they will settle. And by the way, like, I just want to celebrate that when we started this process of figuring out how particles work in treatment plants, we would have had the equation that's on the upper right, the terminal velocity of particle, but we didn't yet have combined with that the notion that, hey, the flocks are all fractals and they have lower density. And so we didn't know how to account for that lower density of these flocks. And now we do. Now we know that they're fractals. We know roughly what that fractal dimension is. And so we can actually predict how fast these particles are going to be settling in our treatment process.